Well, hello, welcome back. Glad you're here. Hope you had a productive and restful break and that you're ready to get started again. Let's jump back into geometry and let's remind ourselves a very fundamental definition of congruence. Two objects are congruent if there exists a series of rigid transformation that maps one onto the other. So, in the case of each of these sets of polygons, it's pretty clear that there is a set of rigid transformations that will map those together. In fact, it's not a very difficult one, right? There's just this slide that maps them onto each other. Sometimes we see some things and we might say, hey, those are congruent to each other, but we got to be careful because even though they look like it, it's pretty clear that there was not a series of rigid transformations that would map those to each other. They're different shapes. Now, we do have things that we call triangle congruence conditions, and there are five of them. These are written on the board in the classroom. And we've introduced those a little bit at a time, but we're at a point right now where when we see one of these five congruence conditions, we can establish that the triangles are congruent by asserting the congruence conditions are true. One of them is angle side angle. So whenever we see this pattern that we have two triangles with a pair of congruent angles, and the side that connects them is congruent, we know that there has to exist a series of rigid transformations that would map one onto the other. That's also true for angle angle side, and angle angle side is actually very related to angle side angle because of the third angle theorem. But when we see this, right, one tick to two ticks and then the congruent side, one tick mark to two tick marks and then this congruent side, we know that there's a series of rigid transformations. In this case, it included a reflection and then a rotation and a slight translation that will map one onto the other. Another triangle congruence condition is side angle side. Here we have two pairs of congruent sides and the angle that's in between them that's congruent. So we know that there has to exist a series of rigid transformations. That pretty much looks like I'm sliding this point to this point and rotating around there to get them to be the same. Then another triangle congruence condition we have is side, side, side. Right? Whenever we see this, we can assert that these triangles are congruent by the side angle side congruence condition. In this case, I think there has to be a reflection again, and then once the reflections happen, then there's a translation and a rotation that'll map one onto the other. And then the final one is hypotenuse leg. We do have to establish that we do indeed have right triangles in this case. Once we know that we have our right triangles, right, and our hypotenuses are congruent. Here you can see that our hypotenuses are marked off with one tick mark. Fun fact, that's always the side that's across from a right angle. It's also the longest side in any right triangle, so these longest sides are congruent. And then you can see I have a pair of congruent legs as well. When we see that, right, we can assert that these two triangles are congruent by hypotenuse leg. Again, it does require three things. They have to be right triangles, and the hypotenuses have to be congruent, and you have to have a pair of congruent legs. So, cautionary tale, just because we've observed this and we played with it in Desmos and we saw that it appears that these triangle congruence conditions always work, and there were a few that we considered that didn't always work. For example, angle, angle, side, and side, side, angle didn't work for a couple of different reasons. But these ones we haven't been able to show that they fail. However, just because something doesn't fail during our observations of that object doesn't mean that it always doesn't fail. That's a weird sentence. So I just want to point out that observations are not proof, right? We haven't proven that these triangle congruence conditions always hold. We've been assuming it. And what I want to do right now, albeit a little bit weak, I want to try and establish that at least one of them holds in all cases. So again, the big idea is that an observation is not a proof, but I think that we can demonstrate in this case that side angle side is indeed always true. And I hope that you see the slight difference in what's happening here. Yes, I see that in this case I do have the side angle side pattern, right? And we're asserting that these are true because they meet one of our accepted triangle congruence conditions. But the question is that triangle congruence condition valid? And if so, what evidence do we have of it? Well, I claim that the only thing that we have to assume is the one idea that if we subject a polygon to one of the three rigid transformations, we get another third, or we get a second congruent polygon to it. So what we're going to do is we're going to say, look, let's just focus on this particular triangle, subject this triangle to a series of rigid transformations, and then see if indeed all these parts have to line up with each other. So we're trying to prove SAS congruence. So we know that congruence means that two triangles have corresponding side lengths and angle measures that are equivalent. So we have to be able to move triangle ABC onto triangle DEF using rigid transformations. Since we know that these rigid transformations preserve both the lengths of the triangles, i.e. AB, as I move it, right, AB is not going to change its side. AB is going to stay this same side. And this angle A is going to stay the same side as I move it. So one of the things we can certainly do is we can move point A onto point D. So no rotation here. This is just a translation. And when I move point A to point D, the only thing that I have now is this second triangle, or it's actually a third triangle, but a second version of triangle A prime or ABC that I call A prime, B prime, C prime. And because that was just a series of rigid transformations, I know that A prime B prime has to be congruent to AB. I know that A prime C prime has to be congruent to AC. And because angle measures are preserved during rigid transformations, I know that angle A prime has to be the same as angle A. So another thing that we can do now is we can take this triangle and we can subject A prime, B prime, C prime to a rotation, right? So when I subject it to a rotation, the only thing that I'm going to claim here is I'm not going to claim that everything's the same size, but I'm going to subject it to this rotation. And now I have this third version of ABC. And I know that that subjecting triangle A prime, B prime, C prime to that rigid transformation called a rotation doesn't change any of the dimensions of triangle A double prime, B double prime, C double prime. It's the same as its two friends, right? So the purple is the same as this orange yellow one, is the same as this green one because of the three rigid transformations. And we do know that there's a ray here, right? So I know that this ray from A double prime to B double prime, that ray AB, remember ray is just something that has a start and then it goes in this direction. We know that this ray and the ray below it, right, ray DE, they're both pointing in the same direction. All that we know is that they're pointing in the same direction. But one of the questions that we don't know is point B really going to lie exactly on top of E, right? We know that they're pointing in the same direction, but are B and E actually in the same spot? And if we think about it for a little bit, let's think about it for a little bit. We know from our original assumption, and you're like, what original assumption? Let's go back. Boom, 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 boom. Right? We know from our original assumption that this length A to B, right, is congruent to D to E. So I'm not going to say that all I'm saying is that this is congruent to this one, right? I'm not saying the whole triangles are congruent. I'm just saying that A to B, the length AB is congruent to the length DE. So what that gives me is because those lengths were congruent, I can certainly say that DE is congruent to AB. Okay. Again, my question is, are E and B double prime exactly at the same spot? Well, they're rays that both start at point D and A double prime. They start there and they point in the same direction, but are they in the same distance? Well, DE is congruent to AB. That was our assumed thing because we assumed we had side angle side. So DE is congruent to AB. AB is congruent to A prime B prime because of the translation, and A prime B prime is congruent to A double prime B double prime because of the translation or rotation in this case. So because of that, right, because AB is congruent to A prime B prime, and because A prime B prime is congruent to A double prime, B double prime. And because originally AB was congruent to DE, we know that, yeah, these 2 points actually have to stop at the exact same location, right? They line up perfectly with each other. So what I have here is I have that D and A double prime line up perfectly with E and B double prime. Okay, that's great, but what about the rest of the triangles? All we've shown is that two segments are congruent. Well, we know that angles are preserved, right, when we subject polygons to rigid transformations also. So I know that this angle A has to be congruent to the angle A prime, has to be congruent to the angle A double prime. So if I think about it, if I start at this segment DE and I rotate out this angle A, I'm always going to land on this same spot right here. And so these angles are the same, right? Angle A is the same as angle D. And the reason why A and D are the same angle is it's because of those transformations. Again, the thing that's really subtle, it's really subtle. It's like so subtle. Like some of you are listening to me talking like Mr. Roberts is absolutely crazy because there's such a subtle distinction here. But I'm not saying that the purple triangle is congruent to the triangle that's underneath it. All I'm saying is the purple one's congruent to the orange one or yellow one, and that's congruent to the green one. And I'm trying to establish, therefore, that this triangle A double prime, B double prime, C double prime meets up exactly with triangle DEF. So these angles are the same because, again, I'm taking, if you go back and think about it, right, I'm taking this triangle and I'm rotating it. And in the act of rotating that same angle, right, those parts land at the exact same spot. So now I've got that this side lines up, right? A double prime, B double prime lines up with DE, and because the rotation preserves the same side, this side's, or this ray, I guess I could say, ray DC or ray DF lines up with ray A double prime, C double prime. So those rays line up. Then the only question is, well, does C have to match up with F? And yeah, the reason's exactly the same, because originally DC, right, or I'm sorry, because originally AC is congruent to DF, and because AC is congruent to A prime C prime, and A prime C prime is congruent to A double prime C double prime, right? Because I've got this congruence train that's going two different directions, right? This is congruent to this, and then underneath all that, AC was congruent to DF. So yeah, they're going to line it up at exactly the same spot. So here's the remarkable thing, right? We just established that because of the rigid transformations, right? Because of the rigid transformations, these two triangles have to be congruent. And it's not just an observation now. It's not just like, oh, it looks like they line up. No, it was annoying to listen to, and I apologize for you listening to it. But it was annoying, and I apologize for it. But there's a fundamental reason underneath that, and it all has to do with transformations preserving congruence of polygons. So at this point, what we're going to say is, okay, this triangle congruence condition, this one we've talked about, side angle side, is not just a triangle congruence condition. It's actually a theorem. And we will now call this, we'll elevate this, and we're going to call it the the side angle side triangle theorem. And when we see this now, it's not just that we've always observed this leads to congruent triangles, right? This proof shows a little bit more of this. I think I am going to be including a written version of this proof as well, and maybe it's a little bit easier if we see this written out on paper. As we turn our attention to our homework, right, I want you to understand that I'm not asking you to prove these theorems, right? So watching, observing, listening to, and suffering through that talk about why that is not just a triangle congruence condition, but why it's actually the side angle side theorem, right? That's not what we have to do with these proofs. What we have to do with these proofs is establish one of the 5 triangle congruence conditions, and if we have that, we're good. So the directions here are for each pair of triangles below, decide whether the triangles are congruent and justify each congruent conclusion with a flowchart. And I think that there are 3 of these that are. So you're going to be doing 3 flowchart proofs. This is a substantial task. And when I look at your work in class, I'm looking for this from this substantial task. I need to see these original diagrams, right? A proof without these diagrams, a flowchart without these is not a flowchart proof. So make sure you do this neatly. The other thing that I need to see is I need to see the flowchart with all of your ovals. Remember, in each one of the ovals, we need to have a reason, and we also need to have a not only do we need to have a reason, but we also need to have a justification for that. Or we need to have statements. I'm sorry, we need to have statements inside the oval and a justification outside of that oval. And then we need to show how those connect with each other with a flowchart. I'm going to choose to do one of these, just one of these with you, and you're going to do the rest on your own. Please use the exact same letters that I have here as you're doing your proofs. In fact, we will just dispense with C already, right? We'll just say, look, if you look at C, clearly I have right triangles. That's great. And I have a leg that's congruent. This leg is 6 and this leg is 6, but that's all I have. So I do not have one of my triangle congruence conditions here. This looks like it was close to hypotenuse leg, but it's not met. So we will not be doing a flowchart proof for C. I'll leave A for you to do. I will point out in D that when you look at it, the fact that these are isosceles triangles gives me something about some base angles being equal. So I know that this angle and this angle have to be equal because this is an isosceles triangle. So since RMS is an isosceles triangle, angle R is congruent to angle M. And if I call that arbitrarily X, or I could call it angle R and M, but they're the same. I could say angle R plus angle M equals 36. Because R and M are the same, I could say angle R plus angle R is 36. And then I could figure out what angle R is. Once I figure out angle R, I think that it's going to be 72 degrees. And at that point, I could do a similar argument over here. Actually, probably a better argument would be because this is isosceles, angle T and angle P have to be congruent. Therefore, angle P has to be 72. And if these are both 72, if I add 72 plus angle A and see what A is from that, I think I get A is 36. So I really just talked through the heart of that proof. Now, listening to that is great, but constructing the proof is where the rubber hits the road. Okay, so let's go ahead and look at part B and see if we can't construct that proof together. Yikes, I hope this works the way it should work. Let me take a look at this here. So let's forward to the next slide. There we go. So one of the things we see from this diagram is that KF is parallel to AT. So let's go ahead and write that down. Line segment KF is parallel to AT. And the reason for that is it's given in my diagram. So I have a pair of parallel lines. But what we said is whenever we talk about parallel lines, the thing we should be looking for is congruent angles. And I know up here that this angle, right, angle K, I can say angle K is congruent. I can't call this one angle A, but I can say it's congruent to angle BAT. And the reason why those are congruent is because those are corresponding angles. So corresponding angles are congruent. If lines are parallel, well, guess what? I've got parallel lines, therefore the corresponding angles are congruent. And we're done. Because what ends up happening is I can certainly get that this angle, right, is congruent to this angle. So these are congruent angles. And they both share angle B. But the thing that I end up with is I just end up with angle, 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 which is not one of our triangle congruence conditions. So guess what? I was trying to help you with 68, but 68, those are not necessarily congruent. So we're gonna stop. We're gonna stop there, and I can see, yeah, obviously they're not necessarily congruent because they're different scales, right? So we will stop there. So again, the big thing I'm looking for, and this is a big chunk of your homework, is I should see very nice proofs for A and D. Make sure you spend a good amount of time looking at and getting solid proofs for those two items. Well, again, welcome back. We're right at 20 minutes, so we're going to stop today. Go ahead and do the homework assignment for section 6. I'm sorry, section 7.6.1. 7 point, no, I'm sorry, 7.1.6, and I'll talk to you tomorrow.